So let's start today's session. So, do you have any specific questions or any doubt?
So, I mean, last session was very helpful in doing the assignments for
Mm-hmm.
sure. I do submitted the assignment.
Okay. Mm-hmm.
One question is generic question I have is like when we see this quantum Hall signature,
Right.
conductivity versus magnetic field, we observe that some of the plateaus are longer than the other.
Okay. Mm-hmm.
You see the length of the plateaus is not same. I mean, if we talk about like say fractional quantum Hall, then also we say that some of the plateaus are longer in length if you than the other.
Right.
So I was thinking what may be the reason behind it. Is it material property or is it something which one can see like as a signature in every object irrespective of
In
the
terms
material
of
we used?
any case, the material always plays a role. But so if we think of resistivity versus magnetic field plot, then as you
Yes.
increase the magnetic field, the plateau length decreases, right? Length in the B basically.
Mm-hmm.
Now, that will actually be clear from a very detailed calculation. Uh,
I see. Do you know some differences I can go for so that I can check?
yes, I will share some references. But
Sure,
have
thank
you
you.
seen Quantum Hall Effect by David Tong? So there is a lecture note series.
Okay, okay. So they said something about because I know about them, but I haven't went through like in
Okay.
like
Mhm.
thoroughly through that. Yes.
Right. So
Mm-hmm.
that
Okay.
is kind of very so there you will not see big derivations in throughout the lectures, but
I see. Mm-hmm.
it's kind of more physically motivated arguments, and that is kind of first handout to the quantum Hall effect. But there are definitely more detailed review articles as well as some books by Girvin. So
Okay.
especially Girvin's book is very detailed uh,
Okay.
in quantum Hall effect.
Okay.
Mainly these, and so this is one, and second is lecture notes on QHE by David Tong.
So I'll try seeing in these resources if I can manage to get the answer. Otherwise, I'll come to you back. Okay. Thanks a lot. Sure.
So the last set of lectures that I have seen, I mean the last week 4, is mostly again not exactly focused on the quantum Hall effect, but as you evolve and go more details about the quantum Hall effects and its topology, it was kind of all 3 lectures was kind of preliminary for those things, especially
Yes.
the tide binding
W-
model
What
for the.
what I found was like it's the lectures are arranged in such a way that the assignment of nth week have its content in n plus one week.
Right,
Uh,
right. So
so
basically it tries to say ki, you try your best, and then if not, then we'll solve in the next set of lectures.
ah, I see. Okay, okay,
That's the way. Yeah, but most of the assignments I think can be solved with the combination of these lecture notes of quantum Hall effect by David Tong, and then the NPTEL lectures, and sometimes we need to refer again go back to the basic solid state physics book, maybe Ascot
sure,
Martin or Ivagan book.
sure. Okay.
So today
So for
we
today's yes was yeah that's what I was going to ask. So today we are having the session on
so
week four.
I'll mostly focus on the tide binding model for graphene, let's say.
Okay.
generally. But so the concept of tide bending model itself is a very deep topics, and I highly urge to read that Ashcroft Marvin books, because what I found is that uh, so all other books, while talks about those models, tide bending models, and every condensed matter theory books has a chapter extensive discussion on tide bending models, but a very clear picture is given, and mathematically also much more rigorous in the Ashcroft model. But nonetheless, that book is sort of gives actual physics and what is really the approximation and where we fail in tide bending and so on. This has been
I
beautifully
see.
described in Ashcroft Marvin, whereas other books sort of fails to fully capture the essence of tide bending model to some extent at
Okay.
least.
Okay.
So I'll briefly mention what it really does. I mean, I'll mention more mathematically, kind of, because physically what we are doing, as in the one of the lectures also says that let's say we have a atoms, some periodic arrangement of atoms. Uh, we are talking in one dimension, but the extension of this in 3D or 2D is just straightforward. These are periodically arranged atoms. Where the periodicity is given by A, and around each atom there is a potential, Coulomb potential basically, where at the atom it basically diverges because V is proportional to 1 by R, Q by 4 pi epsilon naught R. So if I talk about this atom, R equal to 0 at this particular point at the atomic position, and it kind of diverges. Although in physical system there will not be any divergence. This will be smoothed out by some presence of impurity, electronic screening, and so on. But if we talk about only the Coulombic potential without any screening and without any effect of impurity, that always happens to some extent in the physical or the uh, available sample that we can get or create. It always deviates from perfect 1 by r, and it eventually becomes some regular function. So these are potentials, and let's say if we think of simple, let's say 1s, there are only 1s orbital. There can be other orbitals, and there are always in different materials. But if I say there is one s orbital and there are some electrons, let's say maybe two. So for this particular first atom, let's say, the wave function is kind of like this. So let me go to green color. So wave function is concentrated. So wave function for this electron, maybe for the first atom, is concentrated around its own nucleus or the atom, and then this is the case for all the other electrons for the other atoms as well. Now, the tide binding, the main approximation lies here that the electrons are sufficiently tightly bound so that they are essentially not free electrons. So, if you recall, we always start the discussion of solid state physics with the free electron model. Basically, you have band dispersion like h square k square by 2m. So this is energy, and then wave function is given by simply e to the power I k dot r, right? So this is the free electron model, and it doesn't consider any kind of lattice potential or anything. It just says ki the electrons in metals, especially the valence electrons in metals, are essentially they are free to roam around within the metals, So they are given by this free electron energy and wave function. So it doesn't account. So this free electron model doesn't account the effect of periodic potential. Or even if it accounts, then in some particular limit for some particular metals, or in fact most of the metals that conducts electricity, so in low wavelength limit we can approximate wave function, or let's say energy, to be of free particle or parabolic, not everywhere. So this thing will be clear when we actually derive the tide bending Hamiltonian or tide bending energy for a graphene, and when we say low wavelength limit, what do we mean by that? Sorry, low k limit, rather long wavelength limit. So k is simply related to kind of 2 pi by lambda. So k tends to 0 means lambda tends to infinity. So this is long wavelength limit.
So K sets the like boundary of our Brillouin zone, kind of like periodically. And if I say
Uh,
my Brillouin zone collapses, then essentially um, my my electron is like getting a wavelength of infinite.
no, so
Oh,
that's not
I
the
see.
way I think to think about it. So what really
Hmm.
happens is that so let's talk about simple 2D square lattice, or even 1D square lattice will also suffice. But in 2D square lattice, let's say, it, so the dispersion is really like kind of like this. So I'm not talking about the absolute energy scale, because it always so minus 4t minus 2t. So for 2D square lattice, it happens to be cos kxa plus cos kya, right? So this is the k. Now if we put kx ky equal to 0, then energy is minus 40. So I'm not talking about this energy scale. Mainly concerned about the shape of the energy. And so this is the this energy is a plot of this function. Basically minus 40 I have not included, but let's say this is 0. So even not, this is not true, because at kx ky equal to 0, this will be actually minus 40, right? So this is said to be minus 40, let's say. But that's a simple coordinate transformation. That's not the point. The point is key, these are my Brillouin boundary. This is maybe for a square lattice minus pi by a, and this is plus pi by a, right? Now around this k equal to 0, so if I have this, again I'm not writing minus 40 constant term, and then t is the hopping. So we have so to be more clear, we have atomic arrangement like this, and then this distance is a, and we can say that one unit cell. So so this is one unit cell, let's say. If you repeat this, then it will continue to form the whole 2D square lattice. 2D square lattice. And so in this model, where energy equal to minus 2t cos kxa plus cos kya. So we have assumed that there is only one 1s orbital which contributes to this energy. Okay. So if we expand this around k equal to 0, so this is the complete expression of the energy, barring this 4 minus 40 term, constant term. And if you plot this energy versus k, you will have this plot where around the Brillouin zone boundary. So this is the real, so this is, let's say, real space unit cell. And if you actually find out the Brillouin zone, which is again, you have to find B1, B2, B2, B1, B2 are reciprocal lattice vectors, and let's say R1 and R2 we have real space lattice vectors. So in this, in our case, R1 and R2 will simply be A I cap and A J cap, right? Just this one and this one, and simply you will find 2 pi by A I cap and J cap, let's say, in the along y direction as well. So the Brillouin zone boundary, if you construct the Brillouin zone in the K space, then also it will also look like a square with boundary minus pi by A, and this is also pi by A, pi by A. So so what we really see here is that around the zero or the midpoint of the Brillouin zone. So let me draw here. So So let's say this is my Brillouin zone, and this is ky direction, this is kx direction, pi by a minus pi by a, and so on. Sorry. Okay, so what is really happening is that this is my center of the Brillouin zone, kx ky equal to 0, right? And similarly, so this is also pi by a minus pi by a, and so on. So around the midpoint, so this is the midpoint where kx and ky both are 0. So we have like this type of parabolic term and parabolic dispersion. But as we go around the end of the Brillouin zone boundary, let's say, so these are boundary points. This is 1, 2, 3, and 4. Then it becomes a little bit flattish, right? And it's kind of, it has no slope at exactly at the boundary, so it has parallel. Okay, so del epsilon del k is exactly 0 at let's say kx equal to pi by a. Okay, and similarly qi equal to pi by a, and you can actually directly have you can actually directly prove this from this expression also. So when you say that low energy model, or let's say k going to 0 limit, so what we really need to do is that we need to expand this around the kg equal to 0 limit, where we have minus 2t. We will expand cos kxa as 1 minus kx square a square by 2. Similarly for ky, 1 minus ky square plus a square by 2, and this will give me minus 4t plus t a square, let's say kx square plus ky square. So at the k tends to 0 limit, so simply again you ignore this part, so this part is again parabolic or the free electron type. So what this signifies is that around the middle point of Brillouin zone, I am writing in BZ in short, Brillouin zone, the electronic dispersion of 2D square lattice is parabolic. So it depends. So the Brillouin, the dispersion actually depends on the path of the Brillouin zone, or in which part of the Brillouin zone I am in, and this middle point is typically called as gamma point, capital gamma point. So in our case, this is 0, 0. So when you say k tending to 0, that means we are basically focusing on a particular zone of the Brillouin zone. Let's say. Okay, so this is just in comparison that k wave factor is simply written as 2 pi by lambda. Lambda is the wavelength, and then we say k tends to 0 corresponds to the lambda tends to infinity limit. But I always I think this is the better way to more physically understanding this thing. You have the Brillouin zone in the K space, and you can directly correlate or map that where my low energy lies. So around this point, let's say gamma point. So is that clear?
Yes, sir. Thank you.
Now, so this was the tide bending model for square lattice. If you derive, you will get it. So now I'll again go back to this situation where we're discussing that electrons are tightly bound to its atoms, or let's say nucleus, and but essentially so we are improving one by one. So I have actually missed, or I have not mentioned one more step. So if so in any solid state physics book you will see the progression of these things when we discuss the band structure and so on. So first we study that free electron model, the most simplest model, Drude theory kind of thing, where we say ki, in metals electrons are essentially free to move, and that's one of the reason where we can easily understand the conduction of the electricity in metallic system. You just electrons are freely moving, so whenever we apply electric field, it just responds to the electric field, so it gets accelerated, and then there is a electron flow, and the result is conduction in the current.
Yes, sir.
Then we improve upon and say ki this is a very crude model, extremely crude model, and it explains almost nothing apart from the Drude theory of conduction and conductivity and so on. Nonetheless, this was a very successful in terms of understanding simple metallic conduction of electricity. So then we improve upon and say or ask the question that we have this periodic potentials, right, in place of atoms. Let's say these are position of atoms. So what really happens, we have some weak periodic potential. So we'll still be in the basis or wave function of the free electron, which is e to the power I k dot r. This is free electron wave function up to some normalization constant and so on. So and then we so h0 our is basically h square k square by 2m. If you like, these are k are momentum. Then we add a very small perturbation. So this is periodic potential but very small. So small periodic potential. So this chapter is usually known as weak periodic potential. And then third we come to the tide bending approximation. But one important conclusion from this weak periodic potential is that whenever you apply this periodic potential as a perturbation term, you'll find that the system develops gaps. So we have the concept of first Brillouin zone and second Brillouin zone, and in simple free electron model, it will go on like this, right? So this is, let's say, first Brillouin zone, and then second Brillouin zone, and so on. But whenever you take into account whatever small or whatever weak periodic potential in the Hamiltonian, you solve it perturbatively, you will find that up to the first Brillouin zone you have some dispersion, let's say free electron like, and then there is a gap. So this goes like this, and then again it goes like this, somewhat like this. But then the main point is there is a gap at the boundary of the Brillouin zone. So here also something like this, and then at the boundary there is a gap, and then it goes like this again. At the second boundary of the Brillouin zone, again there is a gap, and so on. It goes on. So the effect of whatever weak periodic potential is present, the effect can be summarized in one line, that it creates gap in the spectrum. Unlike free electron, which has kind of, there is no restriction for energy and k, right? As you increase the k, and the energy keeps increasing. That's the free electron dispersion, this term h bar square k square by 2m. Whenever we add this potential term, it will create gaps in the spectrum, and so this will be one band. So if I use different colors, then this will be one band, and then this part and this part will form another one band, because so we are drawing in a second Brillouin, but if we draw in a reduced Brillouin, it will kind of look like this. So this is the first band, this is the second band that I was talking about in the last class also, that there is a formation of band, and this is the band width. So electrons are essentially allowed up to zero energy to this energy, and then this level of energy is forbidden for the electrons. Electrons it cannot reside in this energy region, and then it starts again from this energy range. It goes on like this. It is allowed, and similarly, it will again you will have some from the third Brillouin and so on. So this is the effect of this process second weak periodic potential. And surprise, I mean, importantly, again I'm repeating this thing. This thing will happen whatever weak the periodic potential strength is. It doesn't matter how much weak the periodic potential. Once you give that periodic potential in the Hamiltonian and calculate the energy spectrum, you will find the gap in the spectrum compared to the free electron gas, which is perfectly continuous. And and then we go. So again, so how we are evaluating things. Initially, we had psi k, let's say e to the power I k dot r, right? Perfectly free electron. And then here you will have I k dot r, because we are still considering free electron, but we have added one extra potential, weak periodic potential. So some modification will be there. And now come to the tight binding approximation. Now I say key, so in this weak periodic potential, we are essentially considering this as a initial kind of wave function. So how do you do? If I just state the process, what do you do? You take the free electron wave function k dot r, and then second process you have h equal to h0, which is free electron h bar square k square by 2m. You add v0, and this is perturbative term, perturbation, and you solve the perturbation problem to find new wave function and energy eigenvalues. Okay. And if you see the techniques in any standard book, you have to do the degenerate perturbation theory, because k and k prime, if at the this zone area, k and k prime are same, and you have to I mean the energies are also same, because initially we had this continuous spectrum, so you have to do the degenerate perturbation theory, and so on. So this is the process for the second weak periodic potential thing. So, okay. So this is, let's say, A, B, C. Okay. So these are three processes. So the point I am trying to emphasize, that in the process two itself, weak periodic potential thing also, you started with the free electron model itself, free electron wave function. So you are already assumed that electrons are still free, but there is some effect of the periodics, there are periodic potential, we need to account for that. That's the key idea of this weak periodic potential process. But on the extreme, other extreme, in the process 3, or let's say method 3, tide binding method, we go completely opposite. At the very first we say ki no, electrons are tightly bound, so where is that figure? Yes, so here, so at the very first we say ki electrons are tightly bound with each other, but there is some probability of hopping to the next atom, let's say. So here is an one electron, let's say, for this atom, and then since there will be some overlap, this area, let's say, so this area is overlapping region, so there are finite probability or tunneling probability to the next atom. So these we can consider actually as a tunneling problem, right? You have this potential, this kind of potential, and then there is a barrier, right? So electron have a, let's say, energy at this position, and then you have a barrier up to this energy. This is the highest of the potential, and so electron have to cross this barrier. So it's like this one, right? This one. So electron have to cross this energy barrier to move to the atom 2. So there is some finite electron, tunneling probability of an electron at the first atom, which can go to the second atom, let's say. So this is the key difference, that in tight binding cases we are already starting from the tightly bound atoms, sorry, tightly bound electrons, and the process is simply, uh, we we go ahead with the atomic orbitals formulation. So let's say phi m are my atomic orbitals, which can be s, p, d, f, etc., depending on the how many electrons are there and which electrons I am talking about. So by the way, even in tight bending approximation, let's say I have some atom plus, and then these are electronic orbits, these are electron sorry these are electronic orbits. Those electrons which are deep down and very close to the nucleus, they also do not contribute to this tight binding approximation, because they are so tightly bound, that to the nucleus. That means at that particular atom, that they have almost zero probability of hopping to the next atom. But these outer electrons, let's say outer orbitals, so it can be s, it can be p, it can be d, f, etc., depending on the atoms and its atomic number of electrons and so on. So when we say atomic orbitals of electrons, essentially we mean that those electrons of the outer atomic orbitals, so that there is a finite hopping probability. Any
So
question?
for instance, if I consider say sodium,
Hmm.
and I say I have just one electron, but on the other hand, if I go to cesium, so
Hmm.
are there any, like, does this model also consider that there is just cloud of electron which going to influence the outermost electron, because there are like more electrons now underneath in case of cesium than of sodium. So
Okay, so actually I forgot the cesium's atomic number. So what is that?
I think it's 56, something
Okay,
around, yeah.
56.
So
Okay.
yeah,
So
yeah.
sodium you have
On more,
11, right?
maybe. Yes.
So I have sodium, if I consider, then 1s2, 2s2, 2p6, and then what? Uh, 3s1, right? 11.
Mm-hmm. Yes.
And
Yes.
for cesium, if it becomes 56, let's say, then also,
55.
okay,
It's 55.
55,
Yes.
then I do not know how. So, what is the outermost orbital? It will definitely not be 3, but something else, maybe 4 or 5. But yeah,
Mm-hmm.
what was your question?
So, like, does the model also consider the effect of like electrons which are inside, which
No,
are
no,
not
no, no.
participating, but the
No, it doesn't consider actually, because even if you consider, so
Yes.
these things essentially we I mean evaluate computationally, and in very few
Hmm.
cases you can actually evaluate analytically. One example is graphene, and one I mean simplest example is of course that 2D square lattice or even 1D square lattice, not on the square lattice but on the chain. But the point is key, once it becomes, let's say, even in 11 sodium cases, the problem gets very complicated and it is almost impossible to solve analytically. So there are different methods or different packages for calculating these tide binding approximation. I mean tide binding approximated energy eigenvalues, wave functions, and so on. But even those cases also, they only consider the outermost orbitals. Now in some materials we need to go more inner orbitals. Let's say, I mean, again it depends on how the molecular I mean the molecular orbital gets found, because in the carbon cases, in the I mean graphene cases, you will see that from it is 6 graphene, but it transforms. So when it uh, forms graphene, then it actually happens to it 1s2 2s, so 2s2 and 2p, let's say 2. So that was the pristine carbon. But then when they form graphene, uh, all these are carbon atoms at the corner of this hexagon. So this actually happens to be 2 sp and then 1 pz. This is the molecular orbital formation. So formulation. So this is one. This remains as 1s2. 1s orbital is completely out of their way. But then there is one 2s, right? 2s and three 2p orbitals. Px, py, pz. 2px, 2py, and 2pz. This is for carbon, by the way. And it turns out that when they form this graphene of this particular structure, they form a molecular orbital of this form, where so from this part it happens to be something like this, uh, 2sp2. This is also another 2sp2, and then 1 pz remains there. So let's say then 1 pz. So these may not be correct representation. I'm just showing for convenience that these are three orbitals, one 2s and two uh, p, px and py. So they form a molecular orbital, and then one pz remains kind of as free. And these sp2 orbitals actually form sigma bond, and these pz orbital forms pi bonds in the graphene. Okay. So what I mean is that it depends on the material also, that how the molecular orbit or orbital get forms, and accordingly we have to take into account. So just to give the example that in the tight bending case of graphene, let's say, we do not consider this 2p sorry sp2 orbitals. We only consider these pz orbitals. These are pi bonds. Pi bonds means this is, let's say, my pz orbitals of two adjacent carbon atoms. So these are the bond, kind of parallel bond. Okay. So these are the bonding of pz, whereas sp2 something bond, sorry, bonding looks like, if I'm drawing one lobes of sp2, but there are three lobes like this. So this is the direct bond. So in sp2, so the what is the difference between pi bond and sigma bond? So very roughly we can say that pi bond is a little bit weaker bonds, so their bond strength is lesser than the sigma bonds. Why? Because the overlap region for the sigma bond is greater than the pi z bond, basically. Okay, so the point is it depends how the orbitals forms molecular orbitals, and which orbitals remains as free, or in some materials it can happen that all are form molecular orbitals with strong sigma bonds and so on. So we need to actually evaluate or see what is the actual form of molecular orbital.
I see. My motivation was because you mentioned the fact that there is this transmission. So there is like the tie binding model assumes that the electrons are they're tightly bind to the iron cores,
Hmm.
like iron cores, but then there is a transmission probability amplitude. And I was wondering that does the cloud which they sit on, like the outermost electrons,
Hmm.
going to influence this transmission probability or not? Or does model says about or not? And but okay, you mentioned that okay, it depends. Like they just take care of the electrons which are at the outermost, which again
Yes.
depend
So
upon
again,
the
so ideally,
yeah.
what we do, ideally the process is key finding the transmission probability. I mean, how do I find the transmission probability? The simplest crude way of thinking is the how much is the overlap in the orbitals, right, from the adjacent atoms. If the overlap is
Yes.
extremely less, then transmission probability is going to be less because transmission probability will incorporate some terms like that. Let's say this is the first atom, uh, psi is the wave function, some potential, and then psi second, right? So this kind of term, square of it. So transmission probability or tunneling probability will be proportional to this term. So if this term or the overlap is extremely less, then we can say that there is almost zero tunneling probability. And in many packages, let's say the most sophisticated package or the most sophisticated method to do that right now available is the DFT, density functional theory. This in itself is a big course, but in this DFT, I mean, people do simulation and then uh, so plot band structure and so on. There is something called one-year functions or one-year orbitals. So in our case, we will mostly let's say consider psi, which is a function of k, right? It is extended in the k space, but uh, no, so it is extended in the real space, sorry. So psi k means at a particular k, but it is extended in the real space. Even in the tight binding case also, we'll be writing wave function in this form, which will be extended in the real space. But one year orbitals is the opposite of that. So one year orbitals are exactly opposite of that. So they are very localized in the real space, but extended in the k space. Okay. And so from those on-year orbitals, they can actually, I mean, evaluate or actually infer that how much is the tunneling probability it can be. Because if it is too much concentrated on a particular atom, then definitely tunneling probability will be very less. If it is a little bit extended, then it will be sort of some value which can be significant uh, which will significantly contribute to the formation of tight binding uh, electronic dispersion, let's say. So in the background there are a lot of processes that one need to check. That's why we can actually talk analytically, at least we can actually talk about very few models uh, to deal which we can deal with hand. And let me tell you that even for those models also, it has been verified with some other method, some other simulation, more realistic, more sophisticated simulation, that indeed pz orbitals contributes to the low energy models, and other orbitals are contributing kind of tightly bound, which are not giving me dispersion or not giving me sufficient hopping amplitude at the low energy level. Okay. So in transport, we always talk about low energy level. What do we mean by that is that a system has some intrinsic Fermi energy, right? So the simplest way to think about, uh, at least I think, is that EF Fermi energy is proportional to n to the power 1 by 3, right? For a 3D free electron gas, this is 3D.
Yes.
So So I have some particular, let's say, electron density in the system that depends on the system. So depending on that, I will have some Fermi energy, right? So that will be fixed for that material. If I have the number density fixed, then Fermi energy will also be fixed at a particular
Yes.
temperature. Now we are not talking about
Hmm.
temperature effects and so on. So in transport, most of the cases, the electrons around the Fermi energy matters more. So if we plot the Fermi function, so this is the Fermi function, let's say, and this is energy. So this is the energy. So at the zero energy level, some this will be a very sharp peak, at kBt equal to 0, let's say. And as we increase the temperature, this will be a little bit more smooth, something like this for a kVt which is T1 greater than T equal to 0, let's say, at some finite temperature. So, so whenever we apply some external perturbation, let's say even the electric field, so the electron, so let's talk about the zero temperature case, which is the most easiest to understand here. So I have electrons up to this energy completely filled. Let's say that's at the Fermi energy, which is again determined by the electron density and other some material properties, effective mass and so on. So whenever we give electron, an external perturbation to the system, let's say electric field, then electron will have to go to some energy level which is available for them, right? In quantum mechanics, that's the one difference, that electron cannot reside in any energy level, right? It will have to have some kind of states. So let's say our electron was psi k state, and after giving electric field, it gets excited and it goes to psi k prime state. Okay, this is some state, but this states needs to be available. And so which electrons are more probable to go to a empty state which is available? So these are the electrons with this energy, around the Fermi energy. So this is mu and this is energy. So mu is the chemical potential, or EF. So basically EF is equivalent to mu at temperature 0. Okay, and we are talking about temperature 0. So these electrons around this small strip around the chemical potential are more likely to get activated or get excited and find a new state, excited state, let's say. But electrons at the deep of this Fermi C, let's say, are, they have to spend lot of energy, right? This amount of energy, let's say, if they want to come to this energy, then the electrons from this deep down of the Fermi C needs to spend or absorb this amount of energy compared to this small amount of energy. So that's why in the transport, most of the cases, or in fact all the transports are dominated by the electrons which are uh, which resides around the Fermi energy, and these we call as low energy. Why do we call low energy? Because we most of the time, in fact all the time, we try to plot energy, not the absolute value, but the energy minus EF. EF is the again Fermi energy versus K. So this is just to have a better understanding and clearer picture, that if we have, let's say, I'll show graphene, it happens. So this is, let's say, the graphene's band structure. So E minus EF will look like this, something like this. Okay, so these, so this we call low energy range, where so around the EF, E minus EF we have plotted. So this is the low energy range, and these are the higher energy, right? So so these, so these range, let's say, so these range represents this deep down of the Fermi C. Okay, I hope this is clear.
Yes, sir.
So this is the reason that we are interested in the low energy physics and low energy electrons. Okay, so now let's get back to the tight binding model, and the formulation is the following. So initially we have some block state which are composed of atomic orbitals. So let's say we have atomic orbitals phi m, where again atomic orbitals means s orbital, p orbital, d, f, etc. And then second step we form block states, because so there is a general proof by scientist Bloch that in electronic system, periodic electronic system, uh, whatever be the potential form, exact form of the potential, as long as it is periodic, we will have wave function of this kind. So n is the band index, k is the, let's say, uh, crystal momentum, it will be kind of ik dot r. So this is the free electron part, and unk of r. So this is r. And so in all the periodic cases, we will have wave function for electrons of this form, where unk of r is periodic in lattice dimension r plus, let's say, a or capital, whatever. So this type of form will be there. So from this information, we actually form the block state from this atomic orbitals. So I'll write block state as phi m r k, which is 1 by root over n, I equal to 1 to n to the power I k dot r m I. I'll explain what this terms means. Phi m r minus r m I. So n is basically number of unit cell in the system. So I'll have some particular dimension of material, and then I need to count the number of unit cell, and RMI is the position of mth atomic orbitals. And rest of the things are R is a general position, small r is a general position. And from this we construct electronic wave function. Okay, so this is the block state. So this so this is the block state, and these were the atomic orbitals exactly kind of centered at those atoms. And then in the similar split of this block theorem, we found atomic orbitals of this form, let's say, right? So if we really observe that here we have a e to the power ik dot r term like this one, and then phi m of r term like this one, okay? And this is also repetitive, right? This has a so once you move between the atoms, it can be same. For s orbital, it will get repeated, p orbital, it will get repeated, and so on. And then third process is the formulation of electronic wave function, tight binding electronic wave function rather. So psi j, I'm introducing another new notation, kr or rk equal to m equal to 1 to m. These are two different things. So m is the total number of orbitals in present in the unit cell. Okay, so up to, so let me write, then I'll say c is just a coefficient, and phi m, okay, so this is phi m kr. So from these blocks states, we have formed a electronic wave functions, which are so block state was essentially for a particular atomic orbital, let's say. So from the atomic orbital, we just convoluted with this e to the power ik dot r term and form a block type of so this block type of wave function form. And from this block state, we are essentially adding all the possible atomic orbitals that are present in a system to form a electronic wave function, let's say. So m represents different orbitals, so it can be s, p, d, and so on. Okay, and we work with this atomic sorry electronic wave function. So if we have this electronic wave function, so this is the electronic wave function, then my let's say the Hamiltonian for the system is given by A is, then my energy, so J is the band index, by the way, so J is band index. So my energy for the jth band in the k space is simply given by psi j, which is defined like this, uh, sandwich between Hamiltonian psi j, and in case it is not normalized, just the normalization of psi j. So this is the general procedure of obtaining tight binding uh, energy dispersion relation in k space. So we'll start with atomic orbitals, again consistent with the fact that we are considering the tightly bound at I mean electronic wave function, which is in this case atomic orbitals, which are particularly centered at those atoms, and then from that we form block state in a solid state system, and from block state we kind of take all possible block state. So this was block state for a particular atomic orbitals, and then all possible atomic orbitals present in the Brillouin zone, let's say, or the unit cell. And for this forms the electronic wave function. We just take the uh, basically the inner product of the wave function with the Hamiltonian, which gives me the energy. This is the general procedure. Okay, and the process is not complete yet. Here we need to minimize the energy with respect to the coefficient Cj. So we need to minimize the energy with respect to the Cjm to find the equilibrium energy. So this is kind of a minimization problem. Okay, so I'll just write with respect to Cjm and evaluate energy. And this minimization process actually give you a Hamiltonian it in a form of matrix, because there are different CJM, right? So these will be CJM basis, in the basis of CJM the matrix will be so for so this is, let's say, for band 1 atomic orbitals, again for different bands J plus 1 M and so on. And once you solve this matrix determinants of it, you will get different energy levels depending on the dimension of it. So if it is d by d dimension, then we will have d distinct energy levels, let's say. Okay, so there are quite a few more process involved in order to finally get the energy levels. But I'll just mention the results. So basically, I'm trying to revise a little bit of tight binding model, because in the later part also there is mention of square lattice in presence of magnetic field and how it gives rise to a Hofstadter spectra and so on. Okay, so this is, let's say, equation
So
one. Yeah.
in case when we have like other lattices, for example, Kagome or I don't know,
Hmm.
hexagonal, then this tight binding model also changes or adapt accordingly
Yes, yes. So,
for such.
so, so the system information is already built in from the initial process itself. So the first process is the you choose the atomic orbitals, right? How many atomic
Yes.
orbitals are there in the unit cell, let's say. or
Yes.
the unit cells, and then you form the block state and so on, and then electronic wave function. So depending on the Kagome metals or wild metals or graphene, which atomic orbitals needs to be considered, that
Okay.
information is already in.
And that's always one can find, like, people depend on calculations of DFT, as you mentioned, because
DFT is one of the standard procedure, and it turns out
hmm,
actually the point is ki, we cannot deal with things analytically, right? There are only a
yes, yes,
handful of
yes, yes,
model which
yes.
we can deal
Mhm.
with analytically. So DFT
Okay, I got
comes at those points, or we cannot handle analytically. In fact, the values of this overlap or the tunneling probability, or how much is the overlap and so on, those things also needs to be actually calculated from the DFT. So it's kind of DFT is the
okay.
state of the art machinery to calculate band structure of real materials. But before
Mhm.
DFT, I do not really know what people used to do it.
Okay. Mhm. Yeah. Mhm.
Okay, so from equation 1, if we minimize with respect to CJM, we'll get some Hamiltonian or energy expression equation rather, something like this: H tilde psi j. Again, psi j is the electronic wave function. EJ is the energy. S psi j. Okay. So H prime, sorry, H tilde, we call it transfer integral matrix. So transfer integral matrix, and this matrix S is called overlap matrix. So which is coming from this term. S is coming from the this term, and this is actually given by so this H tilde between two atomic orbitals, let's say mm prime, is simply given by phi m H phi m prime, and then S m m prime is simply given by phi m prime. Now from this expression, we can just so this is the definition of H tilde and SMM prime. So these are the elements of H tilde and S. H tilde and S is the matrix, and these are the matrix element M and M prime. So this will be, so H tilde will be in the orbital basis, let's say. So H tilde in orbital basis. So H tilde will be something like M M M dash M prime and so on. And the band energies are found as determinant of H tilde minus EJ, yeah, and associated with S. S is the overlap matrix. So from this expression, the final formula or the final way to get the energies is that we just need to evaluate the determinant of H tilde minus EJS. EJ are the eigenvalues of this whole matrix. Let's say. Okay, so this form of H tilde is going to be most important thing to derive the graphene tide binding model, let's say, tide binding electronic energy dispersion. Okay, okay, so let's stop discussing tide binding because there are a lot of details, but yeah, so let's go ahead with the graphene tide binding Hamiltonian and how we can derive them. Yes, any question?
No, no, it's okay. Yes, I'll refer to the book you mentioned for the details. If I have questions, I'll come.
Okay. So graphene is an one allotrope of carbon. What do you mean by allotrope? Is that there can be many forms of carbon in the nature, or even we can make it synthetically in the lab. So one is, let's say, graphite, which is nothing but the lot of graphene layers are stacked up on each other so that it becomes bulk. Graphene is one of the example, one of the best example of perfect 2D materials, almost perfect. So ideally for 2D materials, we should not have any C-axis dimension. What do you mean by C-axis? Is the simply Z-axis. So if it is lying in the XY plane, it will have, ideally it will have zero thickness along the Z direction. Nonetheless, it has some thickness. At least the carbon atoms thickness will be there, right? Twice the radius. But this is, if, I mean, 2D materials at the very best example of this is graphene. And the graphene's structure looks like something like this, honeycomb structure, and each place there is one carbon atom sitting, and so on. It goes on. Okay, and these two carbon atoms. So let's focus on one of these honeycomb structure. Let's say, so this is, let's say, one type of atom, and then there is second type of atom also. And although all are carbon atoms, these are also carbon atoms here also. Both the blue and blacks are carbon atoms, but chemically they are actually different. And this type of okay, so bipartite will come later, but the because of the fact that if we go back to here, let's say, so this is my blue and this is my black one. So the environment is different for both the carbon atom, because if we want to understand simply and in a very crude manner, then for this carbon atom, these are the bond directions, let's say, and for black carbon atom, these are the bond direction, right? So they are actually distinct in nature, although they have same chemical composition and so on, but they are not chemically, chemical environment at least is not same. So in one case you have something like this, and in another case this is like this, and there is also alternate double band on the carbon atom. So here, if there is a double band, and then this, and then this. Okay, so if I draw more transparently, then yeah, something like this. So this is, let's say, A type atom of carbon atom, and this is like B type of carbon atom. Okay, and these two carbon atoms are distinct. So the unit cell, what I'm trying to find is the unit cell of this type of structure, and the unit cell is given by something like this. So this should be a rhombus actually. So it's kind of, if I draw here, will be like this. If you repeat this orange colored box, then you will eventually can form the whole graphene lattice system. And note that this graphene unit cell contains both type of carbon atoms. So so this we call, let's say, A type of carbon atoms, B type of carbon atoms, and I mean, it contains both types.
But like inter distance between them changes, because if I say in between black and blue,
Mm, mm.
then I mean I have like two kinds of unit cells.
No, no. Unit cell you consider, or unit cell you define in such a way that if you repeat those unit cell throughout the lattice, you will get the full lattice, right? But
Yes.
once you but if you do not define the unit cell in such a way that its environment is different, I mean, once you move one unit cell away, then if it is different than the previous position, then the unit cell definition is not correct, because you are not able to form the whole lattice with the definition of this unit cell, right? So in the unit cell,
Hmm.
we need to consider both type of patterns, so that the things get repeated, and which kind of reflects the periodicity of the system. But yeah, what was your actual question?
So my question is like, if I consider this black carbon atom at the top of the hexagon,
Hmm,
it goes with the one with the left carbon in the blue.
hmm. Right.
Okay, okay, that okay. Then I okay.
So this actually continues. One with the in the left, one in the right, and then here uh, in the top also there will be only blue, right? So these are happening alternate way.
Yes.
This will be continued.
Mhm.
But
Okay. Yes.
if you repeat this unit cell, then you can form, sorry, you can form the whole I mean the graphene lattice structure like this.
Yes.
Okay. So, and we only consider unit cell atoms. So we'll have, basically we need to find the form of this H tilde and S, and find the determinant of it in order to evaluate the tight binding Hamiltonian. So let's find out what is AHA. So in this case, again in the previous slide, as I said, that H is a, so H tilde is will be a matrix eventually of order m by m. M is the number of orbitals, right?
Yes.
Number of orbitals participating in tight binding model, or let's say approximation. And from the DFT, again we have to go back to the DFT. From the DFT, it turns out that the structure is again 1s, 2sp, and 2pz. This is the formulation of the orbitals. Whenever the graphene, sorry, carbons comes together to form a graphene of this hexagonal structure, this is the atomic orbital formulation, where we'll only talk about the 2pz, because these are tightly bound. 1s is already tightly bound, it is the innermost shell of the for the from the nucleus, and then 2sp2 forms the sigma bond actually. So uh, so let me go back, so let me go to the internet and say how they are look like. I am not sure I am able to convey. So this is the atomic arrangements in graphene, let's say. So the figure A is the normal 1s and px, py, pz. So all orbitals they just draw together. So this is corresponding to the 2s. 1s we do not even talk
Yes.
about, because 1s is the innermost and it is very tightly bound. So we have to allow some amount of probability of hopping also. Tightly bound means it cannot be so tightly that there is hopping probability
Yes.
almost zero. And then B is the, after formulation, the sp2 and pz orbitals. And for a graphene plane, if you see that sp2 orbitals are kind of head on colliding with each other or overlapping with each other, which is represented by this sigma around them. And whereas pi orbitals, or let's say pz orbitals, are vertically aligned, right? So this is the C is the xy plane, let's say, where graphene lies, and then pz are vertically with respect to the xy plane, and these vertical pz orbitals are weakly bounded for the pi 1. So if those are weakly bounded with the atoms, corresponding atoms, then there is a greater probability of the electrons of a particular atom to hop to the next nearest neighbor atoms, let's say, or nearest neighbor at orbitals, let's say. So that's the main idea. Okay. So in analytically formulating the graphene's Hamiltonian and band structure, we will only consider about those vertically pz orbitals. Okay. So okay, so H tilde we need to find. So this will be A orbitals and B orbitals. Okay, actually these are not A orbitals and B orbitals, but let's understand why I am calling A and B. So this is H tilde. Orbital is fixed as pz for both A type atoms, A type carbon atoms, and B type carbon atoms. The orbital that is contributing to the right binding atoms is the pz orbitals, 2pz. Now this 2pz in this unit cell, one is one is this pz orbital and another one is this pz orbitals, right? So one is A type of pz orbitals. So if I write more clearly, let me write A pz orbitals, although the notation is very confusing, and B type of pz orbitals corresponding to the B atom. So I'll have some terms HAA tilde, HB, sorry, AB tilde, and then HBA tilde, and then HBB tilde, right? These are my matrix elements. So here also APZ, BPZ, let's say. So APZ corresponds to pz orbital of A type carbon atom. So what we will find is that HAA, let's say, which is given by we'll use this form of okay. So this form actually, we are in the atomic orbital basis. So we are not using electronic wave function because we are kind of directly using this form, right? So this were done to minimize the minimize the energy with respect to the CJM and so on. But we are directly stepping into this type of formulation where HT is in the orbital basis. So we'll use this type of electronic wave function, let's say. Okay. So for that, what we have is for AA type of pz orbitals, we will have 1 by n, I equal to 1 to n is the number of unit cell in the system, phi a, again this is actually pz orbital of A type atom, minus r ai Hamiltonian phi of A pz orbital r minus ai, sorry, rai. So each A prime is tilde is simply given by this, which we can write epsilon A, some diagonal term. Okay. and this 1 by n comes from the associated 1 by root n with each orbitals, right? From this part we'll have 1 by root n, and from this part we'll have another 1 by root n, let's say. N is the number of unit cell. Similarly, we'll have HBB tilde epsilon b, let's say epsilon b. These we call on-site energy. On-site energy means you are not where you are not interacting with the other type of orbitals, let's say, right? A means the self interaction kind of thing, but although self interaction saying is not a, I mean, right terminology, but these are on site potentials. So what this means is that this epsilon a represents the energy of this place itself. So this place itself, right? The electron has not yet moved from this electron to this electron. H a tilde doesn't represent the hopping. HA tilde is simply saying the what is my energy at the A eighth atom, let's say, A type of carbon atom itself. So this is one site energy. That's why we call it one site energy, which is epsilon A and epsilon B in our case. But since the electrons are essentially, sorry, orbitals are essentially pz, and carbon atoms are also, uh, both are carbon atoms basically at the position A and B, then we often assume that epsilon A is simply equal to epsilon B. So both the on-site energy for the A type of carbon atom and B type of carbon atom are same. Okay, but it is not general, by the way. In some cases, in some other forms of graphene, let's say, because graphene is single layer, right? One layer of carbon atoms arranged in honeycomb lattice structure. If there are more number
Yes.
of layers, let's say, maybe tri-layer, fourth layer, and so on, then there can be on-site energies can be different because of bunch of different reasons. But yeah, okay, so this was one thing, HBB, and then we also need to calculate S overlap matrix element. So if you see from this expression that we need, we need elements of H tilde, and also we need elements of S. Okay, so SAA tilde will be, or not tilde, SAA simply, and SBB will be equal, and they will simply be phi r minus r, phi r minus r, let's say, equal to 1, simply 1, because those atomic orbitals we are at least taking, uh, I mean, so these are the self overlapping terms. So if I have the, let's say, this is A type of carbon atom and have some pz orbital, and I am taking overlap with the same wave function, so psi wave function, psi is a wave function for A type of carbon atom, and then I am just taking the inner product with this side A type of wave function, then it will be simply be 1 if it is normalized, and we assume these are normalized, so this is 1. Now HAA tilde and HBB tilde do not represent the hopping probability. Now the off diagonal matrix element HAB tilde and HBA tilde represents the possibility of hopping between the orbitals of A and B type of carbon atoms. Now let's see what is HAB tilde. Similarly, the complex conjugation of that will be HBA tilde. HAB tilde is simply again 1 by root over n I goes to 1 to n e to the power I k dot r ai phi a r minus r a I sandwich between the Hamiltonian 1 by root over n. Since I is the dummy index, goes over number of unit cell in the atom, so we just change I to j in this second thing of e to the power I k dot r b j and then phi b of r minus r b j. Let's see. Okay, so what does it represent actually? So HAB tilde actually represents, or this above equal, so HAB tilde includes a sum over all the A type of atoms and all the B type of atoms, or let's say all A sites and all B sites present in the system, right? Because I goes over the unit cell, and in one unit cell we have only one A type of atoms, sorry, A type of yeah, carbon atoms and B type of carbon atom, let's say. And since I goes over all the unit
Yes.
cells, so it goes over all possible combination of A and B. Okay, so I think I missed one minus sign somewhere, because these two cannot be same. So what we took initially, okay, so this was plus for phi, so it will be minus here. Okay. Hmm. Okay, now if I let's do one more line, things will be more here. I think 1 by n I sum over I and then sum over j. So this also goes to 1 to n, this also goes to 1 to n, and then okay, let me write this one first. E to the power I k dot r b j minus r a j. So by the way, r, sorry, a I it will be. So r b j and r a I simply represents the position of the B type of atom, B type of jth atom, and it is also A type of ith atom, RAI. And then this is simply phi A of R minus RAI inner product with H phi B R minus RBJ. Okay. Now the important approximation or the interesting part will be this from these two terms. Basically, the main term being this one. Okay. So what this or this bracketed term represents is that it takes the inner product with the Hamiltonian of all possible A type and all possible B type. So so what do we mean by that? If I go back to this drawing, or let me actually have some graphene, yeah, it will be more clear, because the drawing is getting dirtier as I. Okay. Okay, so Oh, this is problematic because this doesn't have identification of A and B. So this is, let's say, A. So all are A, circled are A, and rest are B basically. Okay, so this is enough. So what this bracketed term represents is that it takes overlap with all the A and B type atoms. So this one also, this one also, this one also, and then maybe this one also, all all possible combination. So the point is ki an electron, sorry, I omitted everything. Okay, so the electron of this atom, let's say, it can easily hop. Oh, sorry, sorry. This I have explained completely wrong. What I write and what I say is completely different. It became so. What this expression or this term represents, along with this sum over ij, is that it takes into account of this hopping term, this one, all, all with the, so this is, let's say, A type, and these are non-circled are B type. So all the B type atoms, let's say. Okay, so I need to be more careful because which one is B and which one is A, I need to take. But that
But
is the main essence. Yes.
one small question. So we can always talk about overlap where the hopping is defined,
Right.
no?
Uh, uh,
But so I cannot think like uh, I don't know how I can say this, but if you take like fifth,
hmm, hmm,
uh, then it can go to like the fifth carbon atom, which is in
hmm,
a hexagon. Say
hmm,
if you are counting from the right or the left,
hmm,
it can go all to all the nearby ion sites or atoms which are like linked with a bond,
hmm, hmm.
not not with the others which are not.
Okay, so what we are trying to say is that I should think of probability, or let's say hopping, with only this one, right? Which are
Yes,
linked with
that
the
was
bond.
that's what I
Okay.
was, yeah.
No, actually, in quantum mechanics, we are all kind of say in language of probability. So those with which have stronger links or very close to each other, or there is more and more overlap with the orbital, then of course the overlap will be greater, and so is the tunneling probability. But even if there is 10 to the power minus 10% of probability of overlapping with, let's say, fifth atom's orbital, then also mathematically it is allowed, right? Mathematically it is allowed to have or to hop one electron from, let's say, this atom to go to the this atom, let's say. This is A type and this is B type and this is, let's say, A type. So mathematically it is allowed up to now. So what I was trying to say is that this expression of HB tilde says nothing about which is allowed and which is the small tunneling probability, which have the greater tunneling probability, and so on, right? It is there over, summed over all the possible combination. Now I will take the approximation that it is really very small for a for maybe next nearest neighbor itself. So this hopping probability, this one and this one is quite significant. But once we go, let's say, from this, let's say I am in this atom, so I am not hopping from this one but rather this one. So this is already very small. So that approximation I am going to take right now. Okay, but in principle they are allowed, and in some system, uh, in fact, we need to take into account the next nearest neighbor, next to next nearest neighbor atom. So let's say, so for graphene, so this will be my next nearest neighbor, right? This will be my next nearest neighbor
Yes.
in the pink color, and the orange color is the, I mean, the nearest neighbor, and then next to next nearest neighbor might be uh, somewhere else. Let's say this one, something like this.
Yes. I
then
mean,
some
when we study this crystal structure, we have this coordination number, which I
right.
think gives this information. Yes.
Right, it gives this information, and also the overlap matrix that we calculate from any numerical method, that also gives an idea key, do I really need to care about next to next nearest neighbor hopping elements,
Ah, okay.
or I just need to
Mhm.
cut off from the next nearest neighbor itself. It is, sorry, nearest neighbor itself, it's very sufficient. So that I need to,
Mhm.
so there are
Okay.
lots of checks and balances are there in the DFT process or any other numerical band structure plotting. So sometimes many of the things are automatically done, the code is developed in such a way, and some of the things are we need to take care of manually ki, okay, this is the case, so we need to go ahead in this path or that path, something like this. Okay, so this will this approximation we are going to take, that the dominant contribution, so this overlap matrix, so let me write it. Dominant contribution of the above overlap, it is not actually overlap integral, but rather since it is a Hamiltonian is in between, so I'll simply write phi a, h phi a I, maybe phi b j, so j and I represents the position of the comes from the nearest neighbor hoppings or nearest neighbor atoms, let's say. So we are now going to take this approximation that we are not going to sum over all the I and j, but we'll just sum over. So let's, so how we do it. So h a b tilde, and 1 by n we have sum over, sorry, I, sum over I 1 to n. Now why sum over I is needed, because we are considering the whole system, right? Although we are focused on unit cell, but eventually this sum came up. And here is the approximation term, L equal to 1 2 3. I'll tell you what do I really mean by this. K dot delta L, and then this term phi a r minus r a I h phi b r minus r a I minus of delta L. So what we have really done is that we kept that sum over I as it is, but then sum over j, which was making all possible combination of A and B atoms, we have restricted sum over j goes to L equal to 1 to 3. What it means is that let's say if I focus on this atom, let's say, so I am focusing on this atom, right? And J, I should actually should have done all possible all type of B atoms. So these are, let's say, sorry, these are B atoms, right? So this is the nearest neighbor, and then the next nearest neighbor can also be included. This one, and then this one. Sorry, not this one. Sorry, this one itself, and then this one itself. So these are the all next nearest neighbor. So this is next nearest neighbor. This one is also next. This one is also next nearest neighbor. Okay. Now this was the case when J goes from 1 to n, because it says all type of B atoms also. But we restricted itself to L goes to 1 to 3, and we say that only allowed or only significant hopping are like this one, these three. Okay. So this one maybe we call it delta 1 vector, delta 2 vector, and this one is delta 3 vector. So you also notice that r minus rbj was there, but we have replaced it with r minus rai minus delta l, where we have defined rbi as rai minus delta l. Am I right? So we had rbj minus rai. Okay, so this will be j. So rbj. Okay, so the opposite actually.
There should be plus sign in delta or
Right. So if we take right, so this will be plus sign.
yes.
Then it is consistent, I think. Yes. Okay, so we have restricted ourselves that only these. So for a particular I, let's say I am sitting here. So this circle
Yes.
I, then the only thing matters to me is that delta 1, delta 2, and delta 3. Similarly, I go to another atom. Let's say this one. Again, delta 1, delta 2, and delta
Yes.
3 should matter, and so on. It covers all that.
Hmm.
So
Yes.
this is
So
how
as we
we could.
discussed,
Uh,
like all the possible overlaps boils down to just
Only three.
nearest top three one.
Right.
Okay.
Right.
Yes. Okay.
And this term we call it gamma 0. So this is some energy scale, right? Hamiltonian is energy. Hamiltonian, I mean,
Yes.
dimension is energy. So this is some energy
Yes.
scale which is gamma 0, and this became independent of I because so for all, since our model and the system is isotropic, it doesn't really matter ki you are counting from this ayat or this ayat. So all gives me gamma 0. So this length, sorry, energy scale gives me gamma 0. So that means the whole expression becomes I independent if it is gamma 0 constant.
Yes.
So then
Yes.
this term gives rise to 1 simply, sum over L equal to 1 to 3 e to the power I k dot delta L, and simply gamma 0. Gamma 0 is independent of k, so I can HAB tilde is simply gamma 0, L equal to 1 to 3 e to the power I k dot delta L simply. And similarly, we can easily find out HBA tilde, which will be gamma 0, L equal to 1 to 3 e to the power minus I k dot delta L simply. And sometimes we actually give a name to this function, sorry, if 0 not f of k is simply L equal to 1 to 3 to the power I k dot delta L, then it will be gamma 0 f of k star complex conjugation. Okay. Similarly, we can also evaluate the overlap integral. So remember that in our expression, in this expression, we needed to evaluate h tilde as well as s. So we already had SAA and SBB to be 1, but we have not evaluated SAB. Let's say SAB and SBA. Let's say, which will be SBA star will be SAB. And we similar by similar logic, we can actually have uh, something like S0 f of k, and again f of k is sum over L equal to 1 2 3 e to the power I k dot delta L. Okay. SAB means the overlap between the atomic orbital at A type of atom and B type of atom. So again we are considering uh, the okay, yeah, again we are considering the nearest neighbor atom. The only difference is that So which we are calling as S0, let's say. So let me go back to the S. Things will be clear. So this was my S, right? Let me use different colors. So this was my S. So
Hmm.
without any Hamiltonian in between, this is my S. So now you can think from this expression. So this expression itself. So without any Hamiltonian, so this Hamiltonian will not be there. This Hamiltonian will not be there. Rest of the things are same for SS, SA, or sorry, I'm confusing, SAB actually, because here also A type of atom representation, and here also B type of atomic representation. So only the Hamiltonian will not be there, but otherwise this term will be there, A type and B type. So that's why we got again this term also in SAB and SPA. And S0 simply represents that phi A and phi B, J, let's say, and I, just the inner product of that actually. Okay.
So just one small question. I'm a bit confused. So the element of H tilde, which for example H tilde AB
Hmm.
and SAB, what's the difference essentially?
Yeah.
Because H tilde AB is also telling about the overlap between the two.
Oh,
Uh,
H tilde is telling uh, not exactly the overlap, but it more
ah,
so to be more technically correct, it it actually tells the transferred integral matrix kind of. H tilde we call it transfer integral matrix. So it is not only the overlap, it is actually representing the tunneling, how much is the tunneling probability. So of course the overlap is proportional to the tunneling probability, or the other way around actually. The tunneling probability is proportional to the overlap. But you need some potential, so we are when you are saying essentially that there needs to be tunneling and so on, essentially we are talking about some potential energy, or the energy barrier is there, electron needs to cross, or if electron have that much of energy, then there is a finite probability of that, right? Although in quantum mechanics, the particle has the below energy of that potential barrier, there is finite probability, but those energy information needs to be there in the tunneling probability, right? This is
yes.
represented by Hamiltonian itself. I hope I was clear. So not only overlap integral, but the information of potential also you need, information of the energy of the electrons also you need. So these combined things are represented in the H tilde, let's say.
Yeah, so so H tilde AB essentially has, for example, if I naively think of it, it's having the dimension of energy,
Right,
and
right,
then so it have all the information of the potential, for example, which you
right,
talked about.
right, huh,
And but now S is dimensionless because essentially it's multiplied with E,
right,
which is
huh.
energy.
S is simply just the pure overlap matrix,
So it's a pure overlap matrix.
right, huh.
Okay.
And in tunneling probability, you not only need the overlap matrix, but also some information of potential and so on, right?
Okay. Yes.
And
Yes.
those, and that energy scale, that how what is the energy scale with which it can hop or so on, is represented by this gamma. So gamma, I think around 3 eV for graphene at least. uh, I
Okay.
have to
Okay.
check actually, yeah, most
No.
likely around
No.
3
Yeah.
eV.
No problem. I'll see it. Yes. Okay.
Okay, so this was the S. So we have two Hamilton, sorry, two matrix now, epsilon A, gamma 0 F, sorry, gamma 0 F of k, gamma 0 F star of k, and then epsilon B. And as I said, that epsilon A and B are almost same in our case, isotropic. And S k, S0 F of star k, and 1, right? And for simplicity, let's just assume that epsilon A is simply 0, because this will constant, this will be create a constant shift in the energy spectrum. It is independent of k and so on. So there is nothing to much worry about it. So this is the
First
assumption.
element of
Hmm.
S matrix is 1.
Right, because
Uh,
this is the overlap with the A. So this is kind of self, right? I
with
have A
itself.
type of atom.
Okay, okay. I got it.
That's why
Got
it
it,
is
got it.
only.
Yes.
Now, when I
Okay,
go to
okay.
the B, then I have atom like this. So these are my three. Sorry, if I become more careful, then these are my three delta: delta one, delta two, delta three. So this is, if this is my A, then these are my B type of atoms or at the corners. Then
Yes.
there we have this F star K and Fk kind of things. So now our work is to solve this determinant of H tilde minus epsilon Js 0. Now we take further approximation actually and say that okay, so let me tell you the full story and then we'll see. And if you solve this determinant using this two matrix, you have energy bands like something like this: plus minus gamma 0 f of k, mod f of k rather, and then 1 minus plus s0 f of k, mod f of k again. So this is my energy spectrum for graphene, tight binding graphene. Now people often say, and it is all often found that S0 is also very very much less than 1. So then we take the approximation and say that the energy is simply given by gamma 0 mod of f of k. So this is my tight binding energy for graphene, okay, in this limit. And it has been found that S0 is quite small. If you neglect that term, there is not really much difference in the energy spectrum in terms of explaining experiment as well as other things in theory also. Okay, so then you can simply have two band energy spectrum, right? You have gamma 0 plus minus gamma 0 and mod of f of k means okay, so I have not really derived what is f of k, right? So what will be the f of k actually? F of k is simply given by L equal to 1 to 3 e to the power I k dot delta L. And to determine delta L, we need to, I mean, take some example, in some units, let's say, in Cartesian coordinates. So let me draw it again and
So delta L should be
right.
not the lattice parameter, or
Uh, Delta L is not lattice parameter. It is the nearest neighbor hopping length or hopping parameter, let's say, as much as you can say. So let me
okay.
draw it. Okay, so then it will be better. So, so these are my, let's say, B type of atoms, and these are my, let's say, A type of atoms. And similarly, there will be other things. But so my lattice parameter is this one and this one. So this one is, let's say, call it A2 and A1. Okay, and just to show the other parameters, I mean delta parameters. Okay, I think this is enough. Or no. So these are my delta. So let's call it, this is delta 1 and this is delta 2, all are vectors, and this is, let's say, delta 3. Okay, so these are my nearest neighbor vectors, and this is my lattice vectors. Okay, so remember that lattice form was kind of rhombus type, right? So this will give rise to rhombus kind of thing if we extend in the, so something like this. Okay, so we are interested in finding this form f of k, let's say, and the delta are found to be delta 1 for this picture. According to this picture, if you find, so by the way, these are, let's say, a. Okay, uh, so this carbon carbon distance are a. Okay, so then you will find that delta 1 is a by 2, 1 root 3, and delta 2 is simply a by 2, 1 minus root 3, and delta 3 is simply minus a, 1 0, right? So this is x direction and this is y direction. Okay, so if you put this three things, I mean delta 1, delta 2, and delta 3, then you just need to simplify things. So let's say for l equal to 1, we'll have e to the power I k, where k is only kx and ky, kx I cap plus ky j cap. We are in 2D system, so I k dot delta 1 plus e to the power I k dot delta 2 plus e to the power I k dot delta 3. Okay. Then you will, so after simplification, you will find that something like this form will come, uh, root 3 kya plus 4 cos root 3 by 2 kya cos 3 by 2 kxa. Okay, and you can further simplify it, but nonetheless this is the f of k, and the energy is related to this minus plus minus gamma 0 f of k. Okay, and similarly, so this we assume that only the nearest neighbor hopping elements matters, but rest of the other things are very small, so doesn't need to be considered. But if the question comes, or there is a question, I think, in assignment itself, that derive the graphene Hamiltonian with the next nearest neighbor itself. So so whenever, so one thing, so you may define, or you may go over all of these H A B tilde S matrix, and then say that overlap matrix is really small most of the cases, and so on. That is one way, but most of the time in the solid state physics that we do, we straightforwardly implicitly assume that S is small, so this is, S is small and it needs not to be considered. So we just take the H tilde, we will construct the H tilde matrix and just diagonalize it, or take the determinant of it to find the energy eigenvalue. This is also valid. Okay, we implicitly assume that S matrix has not been considered, and because this is very small, it has very negligible effect on it, on the electronic dispersion. So in the assignment, you can just start by formulating H tilde in presence of next nearest neighbor hopping element. So how do you do it? You just have to start from this expression. You just have to formulate this HAB, right? We have here we have formulated HAB considering only three I mean hopping elements matters, only the nearest neighbor. But next, in the, when it says the next nearest neighbor, you also take into account the next nearest neighbor. Then there will be hopping between the same type of atoms. How do we see that? So in our case, we considered this one, this root, and this root, right? these are the next nearest nearest neighbor. But when it says ki take also account of the fact that there can be next nearest neighbor hopping, then you just go from this to this, right? So this is also B type of atom and this is also B type of atom. So you will get terms in the diagonal elements. Here HAB tilde was off diagonal, so this was HAA, this was HAB, AB and BA and HBB. So you will get some modification, let's say delta HAA, okay, due to this next nearest neighbor hopping. So B to B type of hopping and A to A type of hopping. And I'll just not solve, but I'll just
Okay.
mention the hopping length or hopping this delta type of thing. So if I draw, so this is delta 1, delta 2, delta 3, but let's say let me draw these as next nearest neighbor. N is the next nearest neighbor, so maybe this one is delta 1, and you can have something like so this one is also another one, and similarly there will be somewhere here, okay, this somewhere like this. And these elements sorry deltas, you can just find and match that. I'll again write as prime, so next nearest neighbor hopping vectors. Delta 1 prime will be simply a by 2 1 root 3, and delta 2 sorry, no, this, not this was the for the nearest neighbor. Delta 1 prime will be plus minus a1, and then delta, so there will be 6 next nearest neighbor. Delta 2 prime will be plus minus a2, a1 and a2 is the lattice vector. Delta 3 prime will be plus minus a2 minus a1. This you can simply check, and using this along with the near hopping elements, you just need to incorporate that and you will find the tight binding Hamiltonian incorporating the next nearest neighbor also. And by the way, for this Hamiltonian, uh, right, yes, so you will get some additional term. So if this is the energy, so where is the, so if this was the energy with the next sorry nearest neighbor, then you will get some term gamma 1, let's say, or T prime, whatever you can call it. So you have to take also some, give also some name to the next nearest neighbor hopping elements. What do I mean with that? This is phi a and h phi a, you will get some terms. So this is next nearest neighbor, okay, not the same phi a. This is some at some point, and then the next nearest neighbor. This may, you may give just gamma prime, let's say, not gamma 1, gamma prime, okay, and you will find some term. And the key difference is that once you consider the next nearest neighbor, so let me show, you must have seen already, but graphene band structure. So this is the typical graphene band structure. You will find that there are 6 distinct points where you will find that the so we found two bands, right? One is plus gamma 0, it was there, and minus gamma 0. Yeah, and you'll find 6 points where the bands overlap, sorry, band touches each other. Valence band and conduction band exactly touches at a particular point. And if you see closely, this this band structure is fully symmetric with respect to the zero energy, right? The shape of the conduction band and shape of the valence band is exactly same. This is the case with the nearest neighbor hopping. But when you take next nearest neighbor hoppings, things will change and particle hole symmetry will be broken. So what do you mean by that is that conduction band shown in this figure. Okay, you see that the conduction band goes maybe -7 around, whereas sorry, the valence band goes at -7, and sorry, and the conduction band goes as high as maybe 15, right? So this we call particle hole symmetry broken system, meaning that valence band and conduction band shape are not different. So if you do transport measurement of conduction bands, so let's say electrons which are in conduction band and electrons which are in valence band, you will not see the same response. I mean, the response will be asymmetric, and that's why we call it
Hmm.
particle hole symmetry broken system. We call or we analogy we bring analogy that valence band electrons are kind of holes, and conduction band electrons are kind of just particle and antiparticle function, kind of, just an analogy. Okay, so this is the effect of next nearest neighbor hopping, which breaks the particle hole symmetry in graphing. Okay, so let's
So
stop here. If you have any
yes, just
question,
quick
then yeah, sure.
quick question was so essentially for next nearest neighboring Hamiltonian. I mean, the expression is general. So essentially, we just, if I'm understood correctly, we just need these deltas to be evaluated correctly, and if you put, we get the Hamiltonian.
Right. So you will get two parts, right? One is nearest neighbor that we have already derived in detail.
Yes.
So
Yes.
for assignment problem, don't go over that finding S A S B B. Don't need that. Okay. In
Okay.
quantum spatter
Mm-hmm.
physics, so don't do that. We know, because we know most of the
Mm-hmm.
cases it almost affects nothing. So you
Yes.
start from the HAB tilde. You formulate for the nearest neighbor as it is. I had just
Okay.
formulated. Now,
Yes.
when you make that approximation that j was going to 1 to n, then we approximated, no, no, we are not taking into all those effects. We are only considering ourselves in the nearest neighbor thing.
One, two,
We
three. Yes.
converted it to j to 1 to 3 only.
Uh-huh.
Here
Yes.
you will get another extra. So one part is given by j equal to 1 to 3, sorry, yeah, j converted to l equal to 1 to 3, and then you will get another term which will be l goes to 1 to 6. You will have six nearest neighbor for a particular I atom, and all
Okay.
of
I
those
see.
six nearest neighbor will be with a type of same type of atoms will interact. Okay, so
Mm-hmm.
you just need to take into account of the extra term. That's it.
Okay.
And the corresponding hopping vectors I have already given. If you take the same coordinate system and same lattice structure, graphene structure, then you just take it and use it for the assignment problem.
Okay. Sure. Thank you. And just one last thing for the next week, what topic you plan to, or you haven't decided yet?
I have
Because
not decided
I
yet,
will.
because I actually watch all
Okay.
the video lectures and then decide.
Ah, okay, sure, sure. No problem. Okay. Because I was thinking of also going through quickly so that we can maybe progress faster because, I mean, we are doing good, but in sense like maybe
Okay,
I
so
need
what is
more.
the let me write down my email here. So if you have some particular query, or if you why it is not
Sure, sure.
responding. Uh, what is happening? Okay, so chat is not responding for some reason. So you can write, or maybe let me write. Uh, you can just email me so that it will be also I can prepare accordingly.
Can you see my on the chat?
Yes, yes,
Okay.
yes.
Okay, so okay, I got yours also. Mhm.
So the all small sunitd@itk.ac.in. Okay.
Okay,
So if you
okay.
think
Thank
that
you, sir.
needs to be discussed, you would like to,
Yes,
so just email me at least 2 days before. Okay.
sure, sure. No problem.
Okay. Thank you for
Okay, thanks
sharing.
a lot for your time. Yeah, thanks for your time. Okay, good evening.
Yeah. Good evening.